Hello and welcome. Have you ever looked at a pair of linear equations and just felt stuck? Like it's some kind of unsolvable puzzle? Well, you are in exactly the right place. Today, we're going to break it all down, piece by piece, and turn that confusion into total confidence. All right, let's jump right in.
So here's our roadmap for this explainer. We're going to start with the absolute fundamentals. Then I'll show you a really cool trick to predict what kind of answer you're looking for before you even start solving. After that, we'll dive deep and master the two heavy hitters, substitution and elimination. And to wrap it all up, we'll see what our answers actually look like on a graph and build a little toolkit so you know exactly which method to use every single time.
All right, section 1. Think about it like a mystery. If you've got one unknown, you just need one clue to figure it out. But what happens when you have two unknowns, like x and y? Well, you're going to need two clues, and that is precisely what a pair of linear equations gives you.
Okay, so this is the official form you'll see pretty much everywhere. And don't let those little numbers, the 1s and 2s, throw you off. They're just labels to help us keep the parts of the first equation separate from the second. The real mission here, our entire goal, is to find that one single magic pair of numbers for x and y that makes both of these equations true at the exact same time.
Now for section 2. And honestly, this is one of my favorite parts. What if I told you that you could look into a crystal ball and predict the kind of answer you're going to get before you do any of the hard algebraic work? It's not magic, I promise. It's all about looking at the clues hidden right there in the equations. So here is the big question. Are these two equations going to lead us to one and only one specific answer? Or maybe they actually contradict each other, which would mean there's no solution at all. Or are they secretly the same exact equation, just wearing a disguise, giving us an infinite number of solutions? The secret, it turns out, is all in the ratios of the numbers out front. And this table, this is our crystal ball. It really is that simple. It's all about comparing the ratios of the A's, B's, and C's. If the ratio of the A's is different from the ratio of the B's, bam, you've got one unique solution. The lines will cross. If the A and B ratios are the same but they're different from the C ratio, you've got parallel lines and no solution. And if all three ratios are exactly the same, well then you're looking at the same line, which means infinite solutions. Okay, let's put this to the test with a tough exam-style problem. We need to find a value for k that gives us no solution. So let's look back at our table. The rule for no solution has two parts. First, the A ratio has to equal the B ratio. And second, that ratio has to not equal the C ratio. Let's tackle part 1. Our A's are k and 12, and our B's are 3 and k. So we set it up. K over 12 equals 3 over k. To solve this, we just cross-multiply. K times k is k squared. 12 times 3 is 36. So if k squared is 36, then k could be 6, or it could be negative 6. But hang on, we're not done. This next part is absolutely crucial. We have to check which of these k values also makes the second part of the rule true. Let's test k equals negative 6. The b ratio is 3 over negative 6, which simplifies to negative 1/2. Now for the c ratio, that's k minus 3 over k. So with our value, that's negative 6 minus 3 over negative 6. That's negative 9 over negative 6, which simplifies to positive 3 over 2. So is negative 1/2 not equal to positive 3 over 2? Yes, it absolutely is. So k equals negative 6 is our answer. Just so you know, if you tested k equals positive 6, you'd find both ratios equal 1/2, which would give you infinite solutions. The only answer for no solution is k equals negative 6. All right, let's roll into our first major solving method in section 3, substitution. The name really gives the whole game away. We're going to solve one equation for one of the variables, and then we're going to substitute, or, replace, that variable in the other equation. It's just like subbing a player off the bench to totally change the game.
And here's our 5-step playbook. 1. Pick any equation, and get one variable all by itself. 2. Take what you just found and plug it into the other equation. 3. Hey, look, you've now got a simple equation with just one variable. Solve it. 4. Use that answer to go back and find the value of the second variable. And 5, this is always a smart move, double-check your answer in both original equations, just to be sure you nailed it. Now, here is a pro tip that will save you so much headache. Always scan the equations first. Look for a variable that just has a coefficient of 1 or negative 1. Just a plain x or a negative y. Isolating that variable is so much easier and helps you dodge messy fractions, which is a massive win, especially when the clock is ticking on a test.
All right, let's put this method to work.
Now this problem looks a little intimidating with all those decimals, right? But check this out. We can pull a little trick right at the start. Let's just multiply every single piece of both equations by 10. And poof, just like that, the decimals vanish, and we're left with a much cleaner, friendlier system to solve. 2x plus 3y equals 13, and 4x plus 5y equals 23. So much better.
Okay, time to follow our steps. Let's grab that first equation, 2x plus 3y equals 13, and let's get x by itself. First, we'll subtract 3y from both sides. That gives us 2x equals 13 minus 3y. Then we divide everything by 2, so now we know that x is equal to this whole expression. Now for the key move. We take this entire thing and substitute it right into the x spot in that second equation. So that leaves us with 4 times our big expression, plus 5y equals 23. And look, now we only have one variable to deal with, y. Let's solve it. See that 4 on the outside and the 2 on the bottom? We can simplify that. 4 divided by 2 is just 2. So now our equation is 2 times, in parentheses, 13 minus 3y plus 5y equals 23. Let's distribute that too. That's 26 minus 6y plus 5y equals 23. Combine the y's. Negative 6y plus 5y is just negative y. So 26 minus y is 23. Subtract 26 from both sides, and we get negative y equals negative 3, which means, of course, that y equals positive 3.
And just like that, we're halfway home. We know that y is 3. So to find x, we just plug that 3 back into that handy little expression for x we made a minute ago. So x equals 13 minus 3 times 3, all divided by 2. Well, 3 times 3 is 9, 13 minus 9 is 4, and 4 divided by 2 is 2. There's our final answer. X equals 2. The solution, the point where these two lines meet, is 2, 3. Okay, let's shift gears and check out section 4 and our second powerhouse method, elimination. You know, sometimes substitution can get a little messy, especially with fractions. Elimination is this wonderfully clean, often faster alternative where the goal is to just add the two equations together and make one of the variables completely vanish.
This strategy here is really direct. First, get your equations lined up nice and neat. Second, pick your target. You're either going to get rid of x or get rid of y. Third, and this is the most important part, you multiply one or both of the equations by whatever you need to so the coefficients of your target are opposites, like a positive 4y and a negative 4y. After that, you just add them up, solve what's left, and plug it back in to find the other variable.
Let's see it in action. We've got 3x plus 4y equals 10, and 2x minus 2y equals 2. Looking at these, the y terms are just screaming out to be eliminated. We've got a plus 4y up top. If we could just get a minus 4y on the bottom, they'd cancel out perfectly. And how do we do that? It's easy. We just multiply that entire second equation by 2. So our new system is, the first equation is the same, but the second one becomes 4x minus 4y equals 4.
And now for the magic moment. We just add the two equations together, straight down in columns. 3x plus 4x gives us 7x. Now here it is. Positive 4y plus negative 4y equals 0. The y variable is completely eliminated. It's gone. And on the other side, 10 plus 4 is 14. We're left with this beautifully simple little equation. 7x equals 14. And from here, it's a piece of cake. If 7x is 14, a quick division tells us that x has to be 2. Now we take that and plug it back into either of the original equations. Let's use the first one. 3 times 2 plus 4y equals 10. Okay, that's 6 plus 4y equals 10. We subtract 6 from both sides, leaving 4y equals 4. Well, that means y must be 1. So our solution is the point 2, 1. So we've been deep in the weeds of algebra, right? We've been crunching numbers and finding these solutions. But what does an answer like 2, 1 actually mean? In section 5, we're going to connect these abstract numbers to a picture, and I promise it's all going to click.
That solution we found, it's not just a random pair of numbers. It's a location. It's a specific address on a map, a coordinate plane. Think about it. Each of those linear equations represents a perfectly straight line that goes on forever. Our solution is the one and only point in the entire universe where those two specific lines cross over each other. It's the one thing they have in common. Let's go back to that last problem we solved. The equation 3x plus 4y equals 10, that's the recipe for one specific straight line.
The equation 2x minus 2y equals 2 is the recipe for a completely different straight line. And the algebraic answer we found, 2, 1, isn't some coincidence. If you actually graphed those two lines, you would see them intersect at that precise coordinate. That's what we're actually doing when we solve these systems.
And that brings us to our final section. So we now have two powerful tools in our math toolkit, substitution and elimination. But, being good at math isn't just about knowing how to use the tools. It's about knowing which tool to pick for the job to get it done in the quickest, most efficient way possible. So how do you decide? It's actually pretty simple. You should reach for substitution whenever a variable looks easy to isolate, like it has a 1 or a -1 in front of it, or if one equation is already solved, like y equals 3x minus 5. On the other hand, elimination is your best friend when everything is lined up neatly in standard form and the coefficients are already the same or opposites, or they're easy multiples of each other, just like in that last example we did. So I'll leave you with this final challenge to put your new skills to the test. Take a look at this system right here. Which method would you pick to solve it, and more importantly, why would you pick it? Take a second and look for the clues. Is there an easy variable to isolate? Are the coefficients lined up nicely? Being able to answer that question confidently is the true sign that you've got this mastered. Thanks so much for joining this explainer.